section right here. This is the volumes of revolution. In this lesson, we're going to look at finding the volume of a solid that is generated by revolving a region that is in the XY plane around a specified vertical or horizontal line. Because we're revolving these regions over cross-sectional shapes, the cross-section shapes will be disks or washers. Recall that the volume can be found by the area of the cross-sectional face times dx, integrating that as a dx or a dy. Depending on how the cross-section lies, okay, this is dependent on how the cross-section lies. Also recall that the area of a circle is pi r squared, r being the radius of the circle. The process we follow is very similar to the cross-sections methods that we used in the previous lesson. Okay, so let's take a look at an example and walk you through it. So, here we go. The region bounded by the graph y equals the square root of 4 minus x, the x-axis and the y-axis, is revolved about the x-axis to form a solid with a circular cross-section. Find the volume of the resulting solid. Okay, so just like before, you have to draw the region bounded in the xy plane. Okay, so we do that. Let's go ahead and do that. This is a reflected square root shifted over, so it's basically going to be at 4, and it'll intersect over here at 2. So it's just a parabola that looks like that. Okay, this is my region. This is y equals the square root of 4 minus x. And the next thing I do that's a little bit different from before is once I have this, then I draw in a little curve arrow that indicates the axis that I'm revolving around. I find this to be very useful. I recommend that you do it. And I am identifying the x-axis as the axis I'm going to revolve. So literally what we're doing is we're going to, like, if I grab right here on the x-axis and I start spinning this really, really fast, it's going to spin this shape around and it's going to generate a solid shape. That solid shape, now you don't have to try and draw the three-dimensional shape, I'm just doing it for your purposes. So here's what it would kind of look like. The x-axis would be in the middle. This piece right here is what we had over here. There's another one that comes down here like this because we're revolving it around, and this will produce a circular shape here. Okay, this axis of revolution is the center, goes through the center of each cross shape. Okay, and then these are all going to be little circular cross sections. Okay, and so that's what's going on as we go across. Okay, three-dimensional shape. All right, so just like before, so this is what it's kind of doing. So what we do over here is we draw again our representative segment. Okay, now when I revolve, in revolving, each cross section is a circle. So every cross section is going to be a circle. So that's what you draw off to the side. You got to always draw the cross section face, and that segment is a radius. It will always be a radius of this circle in some fashion. Okay, and the area of a circle is found by pi r squared. Pi r squared, where r is this radius. So I have to find this radius, which is that segment right there. Okay, and it crosses, it's perpendicular to the x-axis, where the axis of revolution, so I'm going to have a dx. So I need to find it in terms of x. Remember, it's found by top minus bottom, so r of x is going to be the square root of 4 minus x minus 0, which is just the square root of 4 minus x. And since my area is pi r squared, and then is my r, then my area in terms of x is going to be pi, and then the square root of 4 minus x squared. We can then simplify this because of the squared aspect, and we get pi times 4 minus x. That is my a of x. Once I know that, then I can do my integration. So my volume is the integration, and we'll do the limits in just a minute, a of x dx, and we're ranging, these things are going to go from 0 to 4. And so then this gives me 0 to 4 of this quantity, pi 4 minus x dx. And at this point, we can work this out by hand. And pi is just the constant. And it'll be that times 4x minus x squared over 2. Evaluate from 0 to 4. And the pi is, again, just the constant out in front. And it's the upper minus the lower. 4 times 0, 0 squared over 2, so that's just going to be 0. And we get our answer here, 16 minus 8, so this is just simply going to be 8 pi. And that's my volume. Okay? Now, I'm going to show you the notes I wrote on this problem so you can see it. There's a lot of notes here, so just pause it and write them all out so you have them, because we're going to follow those lessons, those notes that I just gave you. Okay? So here we go. So here's the problem. I'm going to do it twice. So pause right here, and then I'll move it up, and you can pause again. And then moving it up for the rest. Okay, so there's that example, and there's all the lessons here that we're going to be following, kind of some things for heads up of what's coming. So let's go ahead and look at another example. And so we'll just run through some examples now, showing you different things. So now I have this. This is a region bounded by this graph, 1/2 times the quantity 2 minus x to the third power. The x and y axis, it's revolved around the y-axis this time to form a solid with circular cross sections. Find the volume. So just like before, we need to draw this picture. You have to find this picture. And very quickly here, this is going to be a 2, and here's the 4, and it's a cubic, so basically it's going to come down through here like that, and then go through and come down this way. But we only need the cross up here in the front. We're revolving around the y-axis, so draw the arrow here. This helps you tremendously, because wherever this thing is revolving, your segment has to be perpendicular to it. You have to be perpendicular to the axis of rotation. Okay? So here is my cross section this way, so we know we have to do a dy. That means this is not solved properly. So we need to change this. This is great if I was doing a dx, but for a dy, I need to solve this for x, and in doing so, you're going to get this quantity right here. Just take your time and solve those out. Make sure you can do those. We need to have the circle drawn. So as you saw in the notes I gave you over here, when we draw this, if this segment touches the axis of revolution, we're going to have what's called the disk method. So this is my little r here that I need to find. It is right minus left. Right minus left. So my r of y is going to be 2 minus the cube root of 2y minus 0, or just this part right here. Notice I'm keeping things in these r's and stuff always in parentheses so that you don't forget that this, when you plug into the area, which is pi r squared, I'm going to have to square this quantity. So the area in terms of y is pi 2 minus the cube root of 2y squared. Okay? And so then we can find our volume now. It's the integration. Now, these segments are going from 0 up to 4. So from 0 to 4. A of y, dy. So then we just type in all this. dy. And at this point, I would type it in the calculator and get a decimal answer for this one. Again, we can just multiply this out, multiply this out, distribute it. The pi can come out in front because it's a constant. Integrate each piece. I mean, we can do it. It just, this is easier to do it this way and get this value. So there is your answer there. So again, remember, this segment, if it's perpendicular to the axis of revolution, that tells you if you've got a dy or a dx. So here's another example right here. This region is the x-axis, x equals pi over 2, y is the sine of x, is revolved about the line x equals pi over 2. So now we're not revolving around an x or y axis anymore. So we draw this picture again. You'll notice we're always going to be drawing a picture. Pi over 2. This is a sine curve. So at pi over 2, the sine is 1. At 0, it is 0. So it's basically just this curve like that. And then you have this right here. And that is my axis of revolution also. Okay. Since the axis of revolution is vertical, our cross sections have to go horizontally like that, which means we have a dy. Okay? So, here we go. Because the segment touches the axis of revolution, I know I have a disk method. I'm just going to get solid disks. So I'm going to have a circle. And again, draw your little segment here that represents your radius. So this thing, notice I'm putting it in the same direction. So here's my center. This line is actually that center point. And I just draw it the same way, just to be consistent. We need to take this equation right here and solve for x. So if y equals the sine of x, then I know that x equals the inverse sine of y. So this curve is that curve now. So what is r of y? It is the right minus the left. The right is pi over 2, and the left is the inverse sine of y. Which makes my area pi over 2 minus the inverse sine of y squared. Which makes my volume pi times pi over 2 minus the sine inverse of y squared dy, and the y values are going from 0 to 1. Because remember, we know that point is pi over 2 comma 1. So we know we're going from 0 to 1. Again, good candidate for calculator, and you should double check all these things out to make sure that I typed into my calculator correctly. And there you go. Remember, when you're in sine here, make sure you're in radian mode. Double check your calculator. Make sure you're always in radian mode when you do trig functions of any type. Okay? So this is where the axis of revolution was not an axis, somewhere else. Okay? So then let's look at another thing that's going to happen, just so you know. And that is down here. What happens, oh, by the way, let me just show you these notes real quick. So take a moment, pause, and copy that. Okay, and you can pause and copy that. And then here's what's going to happen next. In this particular case, the washer method. You're going to have the washer method. I said this before. You'll have the washer method when this segment you draw does not touch the axis of revolution. Then you're going to have this. When the representative segment does not touch the axis of revolution, then the cross sections will look like washers, where I have a circle with a inner circle cut out, a donut, a washer, whatever you want to say. And our region is going to be the area between those two, so it's the big circle minus the small circle areas. And so we designate it with a capital R for the big and a lowercase r for the little one. And you need to find both of those. The process is basically the same as the disk method. You can actually think of the disk method as a washer method where the inner circle is 0. There was no inner length, but it's the same process that we're going to follow. Okay, so let's go ahead and look at it. And I got some examples over here we're going to do. So here's our first one. The region is bounded by this curve right here, 2 times the square root of x, y equals 4, and the y-axis. And all of that region is revolved about the x-axis. Find the volume of the resulting solid. So we need to draw this picture. So here is 4. So as I draw this, we have a y equals 4 line. And we have this curve right here. So at 0, we're at 0. And you can go up the line here and figure this out. 1, you're going to be at 2. And if I plug in 4, I'm going to be at 4. So I have this curve that does that. This point up here is 4, 4, 0, 0. And we know that's 0, 4. And this is my region. Okay, this is the area, this is the base that I'm going to revolve about the x-axis. So my little segment has to be perpendicular to that, and thus establishing the fact that it does not touch the axis of revolution right here. So the cross section, if I look at it, once this is generated and revolved around, is going to be a washer. This is always the axis of revolution. It goes right through the center of the whole thing. This is the region where we got to find the area on. So this segment from here to here, so this, that's the area, that's the radius of the big circle, and this is the radius of the little circle. How that translates over here, see this segment right here, right there only, that's that. So the big R is always, in this segment, the longest distance from one tip of this segment to the axis of revolution. That is capital R. Little r is from the other end, the shorter distance between the other end of the segment and the axis of revolution. We need that to help us find and establish big R and little r. Because I'm doing a dx, big R of x is this distance, so it is going to be 4 minus 0, or just 4. Little r of x is from here to here, so that's going to be 2 times the square root of x minus 0, which is just 2 times the square root of x. So my volume is the big area minus the little area. So what is the area of the big circle? Well, it's pi big R squared. That's pi 4 squared, or 16 pi. What's the area of the little circle in terms of x? Well, that's pi little r squared. And little r is 2 times the square root of x squared. And you can simplify that out to be 4 times pi times x. Square the 2, don't forget square the 2, and you square in the square root. And so I have those values. So my volume is pi big R squared minus pi little r squared dx. This circle is going from, on the x, is going from 0 to 4. And so then I can plug all that in. The big one, remember, This is pi r, big R squared. That is that. So that's going to be 16 pi minus 4 pi x dx. Okay? And you can integrate this by hand. It gives me 16 pi times x. And this will be 4 times pi times x squared over 2. And you want to evaluate this between 0 and 4. And you can do all that stuff and you're going to get 32 pi. Or if you do a calculator, you'll get 100.531. Okay, so that is the process you're going to follow there. Now, let's do one more example. This is the last example right here. We got a region bounded by this curve and this line. We're going to revolve it around the line y equals 2. So we got to draw that picture. Take your time. Look for some commonalities between them. We have the line x equals e, so that's going to be right about here. Here's e. So we have that line right there. This is a natural log curve. This is an exponential curve. Here's the line 2. Usually I draw the axis of revolution as a dotted line because it's not really part of my curve and stuff. So doing all this stuff and looking at it and drawing these pictures out, basically what happens is these two graphs are going to cross right here at 1. And it doesn't go all the way up there. So one curve does that, the other curve, the exponential, does this. And this is my region in here. And we're going to revolve this region about this line. So this one up here is the log, so this is the f of x, the natural log of x plus e, and this one right here is the g of x, which is e to the negative 0.5x. And then we're going to draw a representative segment perpendicular to the axis of revolution. This piece from here to here, that's the longest piece, so that's big R. This piece right here is the shorter piece, so that's little r. We draw our washer over here. Okay. And so we have this segment right here. And so we want to find this area of this thing, so we need to find the big R. The big R is the top minus the bottom. The top is 2, the bottom is g of x, which is e to the negative 0.5x. Little r of x is the top minus the other one, which will be the natural log of x plus e. The volume, we are ranging from 0 to e. It is pi big R squared minus pi little r squared dx. And then I can plug those values in. Big R is that. Squared, don't forget to square it. Pi little r, oh, you can't see what I'm writing. E squared, all of that with a dx. You could actually have found them like we did previously, find them off to the side like I did here, which is fine. Or you can do it like this, which is fine. If you do it like this, make sure you write this first and then plug in so that you don't mess up and forget your squareds. You could actually do the squared over here, okay, if you wanted to. Don't call r this thing squared. R is this, and then you're going to square that. At this point, you just use a calculator for this one. This would be a classic example of one that you would do. They would have you set it up, but don't evaluate. They like to do that sometimes. Set up, but don't evaluate. All right? Or you can just use a calculator to evaluate. So if you do that, type it all in, practice typing stuff in, you should get that number right there. And so that's how volumes of revolutions are done in all the different ways. So look at these examples, make sure you write them out. I'm going to move this over so you can get any additional notes that I may have had written out here for this problem. What is r and little r? And then down here, you already have this example. So we'll be doing problems with this in class, and this ends the video.